Welcome back, ladies and gentlemen. We are still in Chapter 12, chi-square tests, and we are now on day 4, the second day in 12.2. We're looking at the chi-square test for homogeneity, and by the end of this lesson, you'll be able to perform a chi-square test for homogeneity. At the end of this lesson, I would like for you to try these problems. Let's go ahead and get started. All right, as stated, we are on 12.2, day 2, chi-square test for homogeneity, and we're basically going to be going through an example in this lesson. So our example is, do women in STEM jobs face a different amount of discrimination as women in non-STEM jobs? A recent Pew report stated that 612 of 1,225 randomly selected women in STEM jobs experienced discrimination in the workplace, while 459 of 1,119 randomly selected women in non-STEM jobs did. Now, letter A is to display the data in a two-way table. All right, so I have one side for whether or not they experience discrimination, so discrimination, no discrimination. And then the other side is whether or not they're in a STEM job, so STEM job, no STEM job. I also have my totals shown to make it easier to find expected counts if I need to. All right, now, it said in the problem that we had 612 of the 1,225 women who were randomly selected from STEM jobs experienced discrimination. So this right here ties into the 612 and the 1,225 that I've written in those places on my table. Now, additionally, we have non-STEM jobs, 459 of 1,119 randomly selected women were experiencing discrimination. So that's where I have this 459 and this 1,119. So that's where the numbers within our problem actually relate in the table. Now, to find the other values, I added the 1,225 to the 1,119 to get 2,344. I subtracted 1,225 and 612, so 1,225 minus 612 to get 613. I subtracted 1,119 minus 459 to get 660. And then I added these across to find these other totals. All right, so you want one variable to be along one side and then your two different populations or groups to be along the other side. Now, to state our appropriate hypotheses for the test of homogeneity, remember, your null hypothesis is a statement of the distributions being the same or there being no difference, and then your alternative is always that there is a difference. So my null hypothesis is that the distribution of discrimination status, because that's the variable that I was measuring, is the same for women in STEM jobs versus non-STEM jobs. So it's the same for the two different populations that I took my samples from. My alternative hypothesis is that the distribution of discrimination status is not the same for women in STEM jobs versus non-STEM jobs. So almost the same statement, it's just one of them says that it is the same, the other says it is not the same. To calculate the chi-square test statistic and p-value, I use technology for this. So if I turn on my calculator, for a two-way table, we need to use the matrix. And I'm going to hit second and then inverse of x, because that's where matrix is written in blue. Go to edit, and I'm going to hit enter on A, and this is a 2x2 table. So I have two parts for my distribution, and I have two different populations that I pulled my information from. So I need 2 and then 2, and then as I type this in, I'm starting in the upper left-hand corner, typing in 612, hitting enter, then 459, enter, 613, enter, and then 660. Now, once I have my table set, I'm going to hit second mode to quit out of this, and then I'm going to go to stat, over to tests. I'm going to go to chi-square test. It asks you where you put your observed counts. It tells you where it's going to put your expected counts. And then when you go down to calculate, it gives you your chi-square test statistic and your p-value. Also, it gives you your degrees of freedom. Now, whenever you're asked for a test statistic and the p-value, you really should identify your degrees of freedom if they're there, because that's what defines the chi-square distribution that your p-value came from. Without that number, you couldn't actually calculate this. All right, so using technology chi-square test, my chi-squared test statistic is about 18.837. My degrees of freedom were 1, and my p-value, which is the probability that chi-square is greater than 18.837, I could use chi-square CDF with a lower bound of 18.837, upper bound of positive infinity, and degrees of freedom 1 to get this value, or I can go ahead and use it from the test. I wrote this down so that you would have that as a reference in your notes. Now, this p-value looks like it's large, and it's larger than can actually exist, so I need to look to the end where it says e-5. Now, this e-5 means that this number should actually be divided by 10 5 times in a row. The first time you divide by 10, the decimal point moves in front of the 1. The remaining 4 times that you divide by 10, you will end up moving your decimal point 4 more places to the left, which is why I have 4 zeros between the decimal point and the 1 when I wrote out the number. So it's 0.0000, so I actually count out those zeros, and then 142. The decimal point originally started after the 1, and I've moved it 1, 2, 3, 4, 5 places to the right because of this times 10 to the -5th. All right, so this is how you'd work through the chi-square test for homogeneity. Now we could also, because this is a two-way 2x2 table, we could also state hypotheses for a two-sample z-test for a difference of proportions. For that, I would have for my null hypothesis that p sub 1 minus p sub 2 equals 0, basically that they're not different. They're the same sort of thing that this says. And then my alternative hypothesis would be p sub 1 minus p sub 2 is not equal to 0. They are not the same. And this would be where p sub 1 is the true proportion of women in STEM jobs who experience discrimination, and p sub 2 is the true proportion of women in non-STEM jobs who experience discrimination. To calculate my z statistic and p-value, I again use technology, so 2-prop z-test. And these are the numbers that I entered into that test. So if I go to stat, go over to tests, and go down to 2-prop z-test, then I'm typing in 612 for the number of women who experience discrimination in STEM jobs. The number of women we asked was 1,225. The number of women in non-STEM jobs who experience discrimination is 459, and the number of women asked was 1,119, and we're looking for not equal to for our alternative hypothesis. Go down to calculate, and we get basically the same sort of thing. Our z-test statistic would be about 4.34, which is what I have here. There are no degrees of freedom for a z-test because z-test is based on the standard normal curve. So we don't need to actually identify that part. But our p-value was again e-5, so I need to divide by 10 5 times, which is why I have 0.0000, so 4 zeros, and then the one I moved around for 2. These p-values are actually identical, and they should be. All right, so you could actually use either one of these tests, depending on what you preferred. Now, if this table were more than a 2x2, if it were like 2x3 or 2x4 or even 3x2, then you could not use the two-sample z-test. The chi-square test for homogeneity is a little bit more versatile because you're allowed to look at more than 2 populations or treatment groups, and you can have categorical distributions that are more than just yes and no. All right? But you could do either test in this situation. So when is a chi-square test for homogeneity equivalent to a two-sample z-test for p sub 1 minus p sub 2? When our alternative hypothesis is two-sided, you do also need to have the not equal to, because that matches with not the same. And there are 2 samples and 2 responses to the category, so a 2x2 table. The chi-square test is always two-sided because we want to find evidence that the distribution is different than what is claimed, and we use a 2-sample z-test for one-sided alternative hypotheses. So if you had greater than or less than, you had a specific direction to the difference, then you would need to use a two-sided 2-sample z-test, or a one-sided 2-sample z-test. If we're just caring about if it's not the same, then we could actually use either. All right, so if we have a 2A table, if it's greater than 2x2, we have to use the chi-square test for homogeneity. All right, go ahead and try these problems, and I'll see you in class.